Violet is 4 by 10. Oh, hey class, it's Dr. Schleich here. I wanted to go over a little bit more about introduction to the physics of waves here and kind of lay out some of these ideas on the whiteboard. So we've got a wave. It is an oscillation. It's a periodic disturbance. And here my marker was the thing being periodically disturbed. So we have an undisturbed equilibrium position. Like if this were a string that weren't being displaced, it would just kind of sit here like this. As it's being oscillated, it moves. It's really important to remember that waves are really just transmitting the energy. There's a transfer of energy through the medium. The particles themselves either move at right angles to the direction of propagation of energy, that's a transverse wave, or the particles are moving along the length of the direction of propagation of energy, a longitudinal wave. So the height of that displacement has a special name. We call it the amplitude. It's the maximum displacement. So the amplitude, sort of looking at it on a waveform, is the distance from undisturbed up to the top of the wave, the crest, or from undisturbed equilibrium position down to the bottom of the wave. Either one of those values could be thought of as the amplitude of the wave. Another important point is sort of what are we looking at here on the x-axis? If it is indeed distance that we're looking at, then the distance from crest to crest we call the wavelength lambda, usually measured in meters. If we're counting the number of waves passing by a point in a second, well then that's the frequency. And so if this wave were passing by my hand, or if my hand passes by these waves, this wave would sort of oscillate, click, 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 click. But a higher frequency wave will always have a shorter wavelength because the waves are closer together. And so now the frequency is click, 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 as my hand passes by the wave there. Another important thing to keep in mind about waves is that if we are not looking at distance on the x-axis, but time rather, then we're really looking at how long it takes the wave to oscillate, or for the wave to move from an identical point to the next one over. And so that is what we call capital T, the time period of the wave. The amount of energy in the wave is related to its amplitude. So if I were to put more energy into an oscillating string by shaking my hand more, then it's going to oscillate a lot more. And so remember that intensity, which for light is like the brightness of the wave, or for sound is like the loudness of the wave, it's related to the energy in the wave. That intensity is proportional to the amplitude of the wave squared. And another important equation to keep in mind is V, the velocity of the wave, is equal to wavelength times frequency. So that's just a quick review of the wave physics so far. I'll be uploading other videos specific to the other learning objectives like Doppler effect and cathode ray oscilloscopes. Be sure to check out the worked examples that I've already uploaded. Oh, which reminds me, we did have a question about one of the other videos where I defined waves as a periodic disturbance characterized by a vibrating medium. And the student asked, well, does it have to be a periodic disturbance? In other words, could a single pulse sent through a medium also be thought of as a wave? Or the question was, is that an example of a wave? And, when you think about it, usually we see waves as a periodic disturbance, but if you send a single pulse of energy through a medium, well, I guess there's like a one-word answer to the question. And that one word is yes. A single pulse sent through a medium could be thought of as a wave. But I suppose there's also maybe a better one-word answer to that question. And that word is cannonball!